Welcome to the second video for section 1.3. In this video we will talk about complex numbers, nth roots, and the product property. So let's start with complex numbers. On this slide, the first definition is for the imaginary number I. I is defined to be the square root of -1. So that's a definition that you definitely want to know. And when you write I, you always write it as a lowercase I. Notice that if we squared both sides of that equation, so we square the I, and we square the square root of -1, we would find that I squared is just -1. If you remember the property that we studied, when we square a square root, we just get the radicand. So that's another important thing to know, is that I squared equals -1. The set of complex numbers are all numbers that are in the form a plus bi, where a and b are real numbers. And the standard form for writing a complex number is with the a first and the bi second. So you may think of I kind of like a variable, and normally we would put a variable term before a constant, but here for complex numbers it's actually the I term second. So for example, if I had the number 4 plus 5i, it would need to be in that order to be in standard form. We do not want to write it as 5i plus 4. That would not be standard form. If we have a number where the a is 0, so maybe we only have just 5i, that is called a pure imaginary number. The complex numbers is a very big set of numbers. It includes real numbers and imaginary numbers. So on this slide, let's look at the left column first. So if we have a number that's in the form of a plus bi, but b is 0, so you don't see the I term, you may just have a number like 2. 2 is actually a complex number because it could be written as 2 plus 0i. Now 2 of course is in many other sets of numbers. Probably you most often would think of 2 as a whole number, which it is, but all the whole numbers are a set inside the complex numbers. It could be a negative number like -5. As long as it can be written in this a plus bi form, it is a complex number. Now on the right column, we have imaginary numbers. So when you can see the I, that is when b is not 0, it is called an imaginary number. So the a could be a non-zero number like we have here, or a could be 0 like we have here. But anytime you see the I term, it's called an imaginary number. So the instructions on these first examples say write each expression as a pure imaginary number. Now, eventually I'm going to have you do this without writing down any work. But to show you why it works the way it does, on this first problem, I'm going to go ahead and show some steps here. And let's rewrite -9 as 9 times -1. We know that 9 times -1 is -9. Now there's a property we're going to look at here in just a little bit called the product property that says this is the same thing as the square root of 9 times the square root of -1. So if we square root the 9, we know that's 3. And on the first slide for this video, we saw square root of -1 is I. So that becomes I. and thus 3i is the answer. So you do not have to show this step or this step. When you see square root of negative 9, you can just say, well, I know square root of 9 is 3, and the negative under the radical becomes an I. It's only when the negative is under the radical that we write it as I. If the negative is outside, it's not I. The negative just comes down when it's outside. So look at number 2. Without writing the steps out, we'd say, okay, I'm going to square root 144, which is a perfect square. Square root of 144 is 12, so the radical comes off because it's a perfect square. And then the negative under the radical we're going to write as I. And so we just write it as 12i. Here it says write each expression as a complex number in standard form. So just remember that means the I term comes second. So these are pretty simple. You're just going to keep that first number, which is your A, and you're going to drop down that sign. This sign right here, you're always going to drop it down. And then we're going to write square root of negative 16 as 4, get rid of that mark there, 4i. So that's our answer. 3 minus 4i is in standard form. So this minus sign comes down. That negative underneath becomes the I. Look at number 2. Keep the 8, keep the addition, and then you write square root of negative 169. Square root of 169 is 13. That's a perfect square. And the negative we write as I. But the sign in front just comes down. It stays the same. It does not multiply by that negative that's underneath. So 8 plus 13i. Here's some that are in fraction form. These problems are again trying to get you ready to use the quadratic formula. So we're just practicing simplifying here. You're going to keep everything on this first step and just rewrite the square root as an imaginary number. So we keep the 15, we keep that minus, then we rewrite square root of negative 25 as 5i. Keep the fraction bar and keep the 5 on bottom. Now there's a couple of ways you could simplify it from here, but I think the easiest way for you guys will be just to take that number that's on bottom and put it underneath each number that's on the top. So we're going to put, sorry about that, we're going to put the 5 under the 15 and the 5 under the 5i. So it splits up into 2 fractions. Then, let's see, if you can simplify each fraction, go ahead and do so. So we can do 15 divided by 5, we know that's 3, we drop down the minus. 5 divided by 5 is 1, and we still have our I, but 1i can be written as just I, since 1 times I is I. So let's write our final answer as 3 minus I. Look at number 4. We're going to start out the same way. Simplify the radical first. Bring down the plus. The negative under is going to become I. Square root of 100 is 10. So we have 10i. On the next step, put the 12 underneath each term that's on the top. So when there's one term on bottom, it goes underneath every term that's on the top. Now this time, the top is not divisible by the bottom. So we go ahead and check, can we simplify the fractions? So for 4/12, we know top and bottom are divisible by 4. So if we divide by 4, we get 1/3. And for 10/12, they're both divisible by 2. So we divide the top and bottom by 2, would be 5/6. The I could be written on the top next to the 5. I would accept it that way. But most of the time you will see it written to the side of the fraction. If there is a fraction in a textbook, you would see the I out to the side next to the fraction bar. Make sure it does not look like the I is in the denominator. It is definitely not in the bottom. So this is in that standard form A plus BI, and you can see the B is 5/6. However, if you wrote it 5I over 6, I would accept that answer as well. Okay, the next part of this video is on nth roots. We've already talked about square roots, but there are other roots, and they would be noted by this number here in that N position. It is called the index. A, as we've already talked about, is called the radicand. When you have a square root, you do not see the index. It is actually an invisible 2. You just don't see it written. So let's review. We know the square root of 25 is 5, since 5 times 5 is 25, or we could say it since 5 squared is 25. So it works similarly for other roots. If we were doing a cube root, which is what it's called when your index is 3, then the answer is a number that to the third power gives you the radicand. So cube root of 64 is 4, since 4 cubed is 64. In other words, since 4 times 4 times 4. And you can go back to that list that we had of perfect cubes, and you just pretty much want to memorize that the cube root of 64 is 4. Memorize all of those that we put in our list. You could do a fourth root. It doesn't have a special name. In fact, any index other than 2 or 3 is just called the root. So the fourth root, fifth root, sixth root, so on. If you want to take a fourth root, the easiest way to do it is to square root twice. So if I want the fourth root of 16, I could start out by saying, well, the square root of 16 is 4, and the square root of 4 is 2. And that would give us this answer here. Now, the reason that that works is because then if you were to take that 2 to the fourth power, you would see you would get 16. And so a fourth root works that way. If you take the answer to the fourth power, it has to equal the radicand. We could go on to fifth and sixth roots, but we're going to stop at fourth root. I won't give you any numbers to take roots of higher than that. Next, let's think a little bit about the difference between a square root and a cube root, which would really end up being the difference between an even index and an odd index. So now these are simple, we've already gone over, but I just want to compare. So square root of 9 we know is 3. If the negative's in front of the radical, we keep that negative sign. And we just learned that if the negative is underneath the square root, we write it as I. So that's how Square root, fourth root, sixth root works, an even index. Now let's look at these cube root examples. The cube root of 8 is 2 because 2 times 2 times 2 is 8. Or in other words, 2 cubed is 8. If the negative sign is in front, you're going to keep that negative sign. If the negative sign is underneath, it is not an I. An odd index will never give an I. I is only for square roots. So when we're thinking about cube root of negative 8, we're trying to think about, well, what number to the third power would equal negative 8? So a number times a number times a number equals negative 8. What about negative 2? There's 3 negatives. Therefore, when we multiply, we're going to get a negative answer, right? Negative 2 times negative 2 is positive 4 times negative 2 gives us a negative 8. So negative 2 cubed is negative 8. So these two have the same answer, but for different reasons. The square root of negative 9 must have the I because there is no way that I can square a number and get a negative. That's why I was defined. Okay, so let's try a few examples. Cube root of 125. So again, I suggest you memorize those numbers that are in that perfect cube list. So you would recognize 125 is a perfect cube and 5 cubed is 125. So the answer is just 5. Fourth root of 81. We're going to square root twice. So square root of 81 is 9 and square root of 9 is 3. Now, if you wanted to check these, let's put the check in purple. Let's check number 1. If my answer is 5, then that means 5 cubed should equal 125. So if you needed to work it out, you could, and you would find it does give you 125. Here on number 2, to check it, we would need to take 3 to the 4th power. So 3 times 3 times 3 times 3, and that does give us 81. This is 9 times 9, 81. Number 3, you've got cube root of a negative. Now remember, the cube root never has an I. Anytime you take an odd root of a negative, it just means you're going to end up with a negative answer. And the cube root of 216 is also in our list, and it's 6. So negative 6. Number 4 is a square root of a negative number. That's the one that involves the I. So you're going to square root 121, which is 11. And the negative underneath is going to be written as I. So these are pretty easy, but it's very important that you know the difference with the cube root of a negative and the square root of a negative. So we've been doing numbers. Let's also talk about variables. We know that in the lists we made of perfect squares, that variables are perfect squares when their exponents are multiples of 2. They're perfect cubes when their exponents are multiples of 3, and you could keep going to perfect 4th powers and so on. The quickest way to take the root of a variable is to divide the exponent by the index. It's just kind of a shortcut way of doing it. Divide the exponent by the index, or root if you prefer to think of it as root. So on number 5, we don't see the index. That means it's a 2. So we're going to take our exponent, 16, and divide it by our index, 2. Or if you prefer, you can think of this as power over root. So 16 divided by 2 is 8. Our answer is x to the 8th. On number 6, we would take our power, 12, divided by our root, 3, and our answer would be x to the 4th power. Now, to show that this really does work, to just do that division, if I were to square x to the 8th, I should get x to the 16th. So x to the 8th squared means x to the 8th times x to the 8th. And when you multiply those, you add the exponents. Or maybe you remember your exponent rules, that when you have a power to another power, those multiply. So you could work it either way. On number 6, if we check, we take x to the 4th to the 3rd power. If you use the exponent rule of a power to a power, you could just say I'm going to multiply those. It'll give me my x to the 12th. Or you could think of it as x to the 4th times x to the 4th times x to the 4th, in which case you would add the exponents. Okay, one more topic in this video. This is an easy property. It works just like you would expect it to. If we're going to multiply two radicals that have the same index, they have to have the same index, then we just multiply the radicands together. And simplify your answers when possible. So on number 1, we both have square roots, and I'm only going to give you those that have the same index. So we keep a square root, and we multiply the 2 times 3. 6 is not a perfect square. That's as far as it goes. Square root of 6 is the answer. On number 2, they're both square roots, so we keep the square root. We multiply 7 times 7, which is 49. Now this time we do have a perfect square, so go ahead and square root the 49, which is 7. The radical comes off. Let's go back to black. Number 3, very similar to number 2. Square roots, we multiply the 5s. We have a perfect square, so we're going to go ahead and square root, and the radical comes off. Now, let's put those two examples together. When we did square root of 7 times square root of 7, we got 7. When we did square root of 5 times square root of 5, we got 5. And it's always going to work that way, because if the radicand's the same and you're multiplying, you're basically squaring it. So now you're square rooting a perfect square. So it doesn't matter what number we put under there. We could put, I don't know, 119 times square root of 119. Then the radical would just come off. So with that in mind, on number 4, square root of x times square root of x is just x. Number 5, same thing. They're exactly the same underneath, and so the radical comes off, and you get just the x minus 3. And when we do these multiplication problems, I won't have you worry about the absolute value bars. We'll just assume that the variables are positive, and that will be written in the instructions. Now, number 6, we're multiplying, and we've got numbers in front of the radicals. So what I would do here is multiply those two numbers that are in front together. So you're going to multiply 4 times 2. And then you're going to keep that square root symbol and multiply the numbers underneath. 3 times 7 is 21. 21 is not a perfect square, so that's it. It just stays as 8 times the square root of 21. Okay, I'm going to stop there on this video, and we'll pick up with simplifying in the third video.